Lesson 1-6, Graphs of Parent Functions. Parent functions are the basic functions that all the other functions are made out of using transformations. Our first parent function is the constant function, f of x equals c, where c is the y-intercept. It's a horizontal line, so in this case it'd be f of x equals 2. Notice the graph goes all the way from left to right, which means the domain is all real numbers. And the range is just whatever y value we have there, just a single element. It is constant, it's not increasing or decreasing. And it is symmetric over the y-axis. Next is the identity function, or linear, if you'd like. It's f of x equals x or y equals x. It goes all the way from left to right, so the domain is all real numbers, and it goes all the way from top to bottom, so the range is also all real numbers. It's constantly increasing and is symmetric about the origin. Then we have the absolute value function. Its graph looks like a V. The y's are all positive because it's the absolute value of whatever x is. Goes all the way from left to right on the graph, so the domain is all real numbers. But the range is just the positive number, so it starts at 0 and increases from there. It's decreasing on the left, increasing on the right, and is symmetric over the y-axis. Next is the quadratic function, which graph looks like a parabola or is a parabola. It does go all the way from left to right. It'll continue going left and continue going towards the right. So the domain is all real numbers. But when you square negative numbers, you get positives. So the range is all the non-negatives, or from 0 and up. It's decreasing on the left, increasing on the right, and symmetric over the y-axis. Then we have the cubic function, f of x equals x cubed. It will continue going off left and right, so the domain is all real numbers. You can fill in any number for the x and get a number for y. It goes all the way top to bottom, so the range is also all real numbers. It is always increasing and is symmetric about the origin. It means if you rotate it 180 degrees, it'll look the same. The reciprocal function, f of x equals 1 over x. It has two asymptotes, the blue dotted lines in the graph. Those are lines that a graph approaches at the edges of the graph. So notice we cannot divide by 0, so the domain will be everything except for 0. And this fraction 1 over something will never equal 0, so the range is also everything except 0. It's decreasing everywhere where there is a graph, so the left and the right's decreasing. And it's symmetric about the origin. You rotate it 180 degrees, it will look the same. Or if you reflect it over the line y equals x or y equals negative x, you'll also get the same thing. Then we have the reciprocal squared function, 1 over x squared, which means when we square any negative numbers, it becomes positive. We still have the asymptotes. We still can't divide by 0, so the domain will be everything except for 0. But now, the range is just the positive numbers and not equal to 0. It'll approach 0 as the x values get very large, but the function will never equal 0. It's increasing on the left, decreasing on the right, and is symmetric over the y-axis. And then the square root function, f of x equals the square root of x. Notice this one's different, as in it starts right there at 0, 0. So the domain is 0 or greater, and the range is also 0 or greater. It's always increasing, and it has no symmetry. Then the cube root function, cube root of x. It goes all the way from left to right in the graph. We can take the cube root of any number. The domain is all real numbers. And the range is also all real numbers. It's always increasing and is symmetric about the origin. You can make more complicated functions with piecewise functions, which we had in the last lesson of how to evaluate them. Remember, it's more than one function put together, each with their own domains. When you graph them, though, at the boundary between the domains, if it's equal to, you put a solid dot. If it's not equal to, an open dot. So let's graph this. So notice the boundary here is when x is 1. So I'm going to kind of put a dotted line there where x is 1. So that's my boundary. When x is less than or equal to 1, so that's this one, we would put the top function, which is 3x. Y equals 3x. So that's linear. The y-intercept is 0, and the slope is 3. mx plus b. So I go up 3 over 1, or down 3 and backwards 1. And I graph this until I hit the boundary. At the boundary between the domains, though, I have to decide, is the top one equal? So the top one is less than or equal to. So that means it's the equal to, so we'll put the solid dot there. On the right side, we're going to use the bottom function. And maybe we will just make a table for this one. Start at 1. I know it doesn't include 1, but it gets anything greater than 1. So 1.000001, or essentially 1. So if I plug in a 1 into the bottom, 1 squared is 1. But it's not equal to, so we're going to put an open circle there, because it's not equal to. I think if I put in a 2, 2 squared is 4. If I put in a 3, 3 squared is 9, and that's off my graph. So then it's something like that. Should be slightly curved since it's part of a parabola. So to graph piecewise functions, you just kind of you put dotted lines at the boundaries, and then you graph each function within its own little domain, and you go up to the boundary on each function. Each function goes all the way to the boundary. If it has the equal to at the boundary, you fill in the dot, like up here. If it's not equal to, it's an open dot, like down there.